Say we have an irreducible polynomial p over a field f, and then alpha is a root of this polynomial. So then you can construct this field f alpha like this. So this immediately implies that this degree of extension of f alpha over f is precisely the degree of this polynomial. So we know the basis of this space is 1 x bar square all the way to x bar n minus 1, where the degree of polynomial is n. So notice that this x bar was our standard notation of x plus our irreducible polynomial. Say for example, this degree of extension of q root 2 over q is 2. So where this minimal polynomial is x square minus 2, which lies over this q. So this q and this q. So again, your joint square root of 3 to rationals over rationals again is 2. Again your minimal polynomial same as x square minus 3 over this rationals. Now we can extend this example. So this we can extend further. Say you now have rationals adjoin root 2 and root 3 to it over rationals adjoining root 2 it. This is again 2. So what is the minimal polynomial? It is again x square minus 3. Now this lies in this field. So x square minus 3 lies over rationals adjoined with root 2. So notice this is here and this is here, and that's how you have this 2, which is this 2 right here. So before you can do this, you have to also show that root 3 actually does not lie within this. So only then you can say that this is a minimal or irreducible polynomial here. So this is irreducible polynomial here. So now we can adjoin this is just this, which is 2, and then you have this, which is again 2 here. So 2 times 2 gives you 4, and that is precisely, so these two would cancel out, so you get rationals, you adjoin root 2 and root 3 to it over rationals is precisely 4. So the splitting field for this polynomial x square minus 2, x square minus 3, and this polynomial is over rationals. This is precisely you adjoin root 2 and root 3 to rationals. So this splits like this. So notice that this is not an irreducible polynomial. Obviously it's a product of two factors, and we have already seen that the degree of extension of this over q is 4. So we could not have used this directly here because here you're talking about irreducible polynomials, and this is not irreducible. It's a product of two irreducible polynomials. So now you can see that this is a separable polynomial because it has a distinct roots. So thus this rationals root 2 root 3 over rationals is a Galois extension. So this is a Galois extension precisely because of this result here. This k over f is Galois if and only if k is splitting field for some polynomial. So the sum polynomial here is this polynomial, and this k is splitting field is this. So this is our k here in this equation, and f is just rationals. So you have this k over f is therefore Galois because we have been able to find a separable polynomial here. So we have a Galois extension. So the Galois group, or the group of automorphisms of this rationals adjoined with root 2 and root 3 over rationals, this is generated by two elements. One is var phi and another is phi. So what do these two elements do? So var phi will act on the roots of x square minus 2. So first irreducible polynomial. So var phi permutes the roots of first irreducible polynomial, sending square root of 2 to minus square root of 2. Does not do anything on root 3 because again you have this action only on irreducible polynomials. Phi on the other hand sends square root of 3 to minus square root of 3. So this acts on the polynomial x square minus 3. So notice that what about root 6? So root 6 you can write as root 2 times root 3. So So product of minus square root of 2 times minus square root of 3 will give you square root of 6. So let us rewrite this var phi and phi. So var phi sends square root of 2 to minus square root of 2, keeps square root of 3 as such. Phi sends square root of 3 to minus square root of 3, keeps the square root of 2 as such. So when it is acting on here, on this product, so first var phi will just keep square root of 3 constant and give you minus square root of 2. Now second time, now phi will act, it will just keep this term constant and convert this square root of 3 to minus square root of 3, giving you root of 6. So this basically fixes square root of 6. Now let us come to the Galois correspondence between the two diagrams. So first notice that you have this identity map here. It fixes this entire splitting field. This rationals are joined with root 2 and root 3. Now this phi, this fixes square root of 2. So corresponding to the field generated by this element phi, you have this rationals are joined root 2, because this phi is going to fix square root of 2. Again var phi fixes square root of 3. So corresponding to that, you have field rationals root 3, because it's going to fix this root 3. Obviously we are talking about automorphisms of this field here. We are talking about automorphisms of this field here, in which this is fixed. So again this var phi corresponds to here. So automorphisms of this rationals root 2 root 3. So it's fixing root 3. That is what it is fixing. And then this we see phi and var phi fixes root 6. So phi and var phi fixes root 6 you have here. And then both of them taken together, they will permute both root 2 and root 3. So only thing they are going to fix is the rational numbers. So you have this. So now you can see the inclusions here. So rationals root 2 will contain rationals, this will contain rationals, this will contain rationals. On the other hand, this phi is contained within here, this is contained within here, this is contained within here. Obviously this is a product, so this is a product here. So now you can check that all these subgroup generated by this, subgroup generated by this, subgroup generated by this is a normal subgroup of this. So since it's a normal subgroup of this, this is a degree 4. So you know that the degree of this is 4, because this is the group which fixes rationals. So this is the group which fixes rational. This is the group which fixes rationals. So you have 4 here. So this degree is 4, and you can check all of these have degree 2. So correspondingly here you get this extension, this degree is 2, corresponding to the polynomial x square minus 2, you have degree 2. This you have again degree 2 corresponding to the polynomial x square minus 6. This again you have degree 2 corresponding to the polynomial x square minus 3. So again further you have over here you have x square minus 3, as you can see x square minus 3. So you have x square minus 3 is our minimal polynomial, degree is 2. Here you can either take x square minus 2 or x square minus 3 as the minimal polynomial, because you cannot actually separate square root of 2 or square root of 3 here inside this field. So you can take any of these polynomials, either x square minus 3 or x square minus 2. You will have 2 here. Again you will have 2 here, which is corresponding to the polynomial x square minus 2. Just like here, x square minus 3 in this, you have x square minus 2. So again all these are of degree 2. You will have 2 here, 2 here, 2 here. So all 3 of these are normal. All 3 of these are normal. So this is a normal subgroup of this. So say this H is a normal subgroup of this if and only if KH over F is a Galois extension. So this is a normal subgroup of this, you can check. This is a normal subgroup of this, you can check. This is a normal subgroup of this, you can check. So all these are Galois extensions. So root 2 are joined to rationals over rationals. This is a Galois extension. Now this is a Galois extension. You can check again, check by this theorem, K over F. So here now we are talking about K is q root 2 over q. This is Galois if and only if this, now we are talking about q root 2. This is a splitting field for some separable polynomial. Separable polynomial is x square minus 2. So we have been able to find separable polynomials like this. And this is a splitting field of it because it contains both minus root 2 and root 2. So similarly here x square minus 6, here x square minus 3. Similarly here. So everything is normal here. This is normal subgroup of this, this is normal subgroup of this, this is normal subgroup of this, this is normal subgroup of this. Obviously identity is always a normal subgroup. So first, this is always clear. The problem arises here. So this you can check by hand that you have a normal subgroup here, normal subgroup here, and normal subgroup here.